Okay, we can start. Paolo, please take a seat. We have this open discussion session for approximately 1 hour where you can ask any question to the speakers on the talks, but also broader questions. And as a rule that we also followed in the previous weeks and it worked pretty well, if you have a new point, new question, you raise your hand. If you have a follow-up, you raise your finger. Okay, so there is a question by Robert.
I had a question about this quadratic gravity. So, is it naturally asymptotically safe? Because you didn't use the word asymptotically safe, you used a different word. You had the coupling constant going down in the ultraviolet. And you called it, you didn't use the word asymptotically safe, you used a different word. Free.
Yeah. So, yeah. So
the question is that a consequence? Does that happen for all of these quadratic? Is this a consequence of this quadratic gravity erosion?
So I did use.
Now these.
I'm sorry, I wasn't here.
Yeah, the two parameters.
Yeah.
And then, so this is a question of ignorance. So my question is simply, in that two-parameter class of model that we're considering, do you get asymptotic freedom?
So asymptotic freedom is actually, let's say, under debate now because there is an old calculation by Avramidi and others that stated that asymptotic freedom occurs for a tachyonic value of the mass of the scalar component of the metric, what I call omega, the one that corresponds to r squared. But recently, this result was criticized by Donoghue, Percacci, and a PhD student of Percacci. I don't remember the name now. And there was, I think, a talk last week or the second week, I don't remember, presenting these results. And they found that actually, with some different definition of the renormalization group, it's possible to have asymptotic freedom also for non-tachyonic values of this mass. Now, coming back to your question, in both cases, there is a region of parameter space where asymptotic freedom does not occur. And there is a region of parameter space where it does occur. So it's not always true that the theory is asymptotically free for any values of the parameters.
The other question is about the curvature of the Bob squared term, right? That's asymptotically free.
That's asymptotically free. Yeah, that's asymptotically free for non-tachyonic values of the abnormal graviton in both results. Yeah, that's true. Yeah.
It's not clear to me why anybody gets excited about the scalar unless you want to be greedy and try to do inflation.
So you are thinking that maybe it would have been better than the other result. What? So it's still possible. It's still possible that for very large values of the coupling that is non-perturbative, then you have an asymptotically safe behavior. This is not excluded. It's just that if you assume, so what I said is true if you assume small values of the coefficients that I've introduced before, F2 and F0, remember? But if these coefficients are large, then maybe there is some asymptotically safe behavior that is not excluded a priori. And maybe there is not even a ghost in that case. This is not proved. It's an open possibility.
Asymptotic freedom means that you write the coefficients of the curvature squared terms as 1 over something squared. Right? That's the way you write it, just style, like Yang-Mills. And then asymptotic freedom means that downstairs coefficient goes to 0.
Yeah, exactly. This is what I call
That's the issue of safety yet. Safety is that you're talking about some non-Gaussian fixture.
Yeah, yeah.
Right. So, but then there are two other parameters, which is the Newton's constant and the cosmological constant. So what Niedermeyer showed at the one loop level is that you have not every coefficient going to 0. So there are non-zero values for Newton's constant and the cosmological constant. That's what safety means here. It's about the other two coefficients. The two that are going to 0. It's not what people call safety because it's sort of Gaussian. So that's the distinction. It's just language. But now, can you also do it if you like asymptotic freedom for both of them? Then there is this dispute about the Weil squared, curvature squared term, because you might like to do Starobinski with it.
Mm-hmm.
Have an inflation.
I guess.
Is it?
The function without any fine tuning, so you have R plus the two terms that you were considering, then generically is Newton's constant going to 0? That was English.
Well, Newton constant is a dimensionful parameter. So generically, is not the running of the Newton constant is not physical. You have to construct a dimensionless quantity, like a ratio between m Planck to the 4th divided by the cosmological constant, stuff like this. Because in general,
scale mu, right?
Mm-hmm.
Define dimensionless ratios. You talk about all renormalizations in terms of dimensionless quantities, right?
Yeah, but we found that if you look at the RGE for these dimensionful quantities, you get a gauge-dependent result, and the gauge dependence cancels only if you take the ratios of this dimensionful quantity divided by a quantity with the same dimension, such that the ratio is dimensionless. In that case, the gauge dependence cancels. Otherwise, you have gauge dependence. So this is a reflection of the fact that dimensionful quantities. So basically, in gravity, the physical quantities are dimensionless ratios. You can redefine the Planck scale and the cosmological constant by an overall factor, such that the dimensionless ratio of the two are the same, and you get the same physics. You can rescale all dimensionful quantities in gravity by the same factor to the power of the dimension of the quantity you're considering, and you get the same physics. But coming back to your question, I also wanted to say that asymptotic safety is actually one of my motivations for considering this non-perturbative definition of the theory, because asymptotic safety could occur. I've not proved it, but it could occur in a non-perturbative regime of the theory. So first, you have to define the theory non-perturbatively.
Yes. Clear. So we define your Newton's coupling, so becomes dimensionless, then goes to 0.
Dimensionless ratio between the Newton constant and
I mean, whatever is gauge variant.
Well, I don't know the answer to this question. I haven't tried to compute the UV limit. In this case.
But
No, but
well, I mean, the one that so say if I would be scattering.
No, I don't know anybody who's talked particularly about asymptotic freedom in that parameter. It's more about curvature squared terms, asymptotic freedom discussion.
So the coefficient in front of this.
yeah,
Weil squared.
yeah, because the rest acts like a mass terms, roughly speaking. In this theory, the Einstein-Hilbert term and the cosmological constant, they behave in the UV limit like some sort of mass terms, roughly speaking. So what is important to establish the asymptotic freedom is the behavior of the coefficients of the R squared and W squared terms.
Because they would be like a coupling constant, right? If I think of
So I kind of missed your talk, but there are various approaches to quantization. You can decide to include the curvature squared terms in the propagator from the start or not. And then so there are two camps here.
Yeah.
Niedermeyer included them, so renormalizing it as a higher derivative theory. And then Abrahamidi and Barvinsky and Tolvin first.
Yeah, but
Made a mistake, but Abrahamidi and Barvinsky have the right numbers, but the problem is it's the meaning of the R squared term. But you are talking in the context of actually starting with the curvature squared terms
yeah, but you can take a limit where the W squared term decouples in the formulation. So you were not there, but in the formulation I gave with the path integral, you can take a limit where the W squared term goes to 0. The coefficient basically is the coefficient in front of the W squared term going to 0. The bare coefficient in front of the W squared term going to 0. So you can take a limit where you get Starobinsky theory, where you just get R squared in addition to the Einstein-Hilbert cosmological constant terms.
There's also then most people who talk about asymptotic safety don't do that. Representatives.
Yeah.
The rest of the world. They just start with the Einstein action, and then of course it's non-renormalizable and it generates counter terms, but you can discuss the possibility of asymptotic safety now, meaning a non-Gaussian fixed point somewhere in parameter space of all this infinite number of parameters. And what I understand from Daniel Litin in Sussex is that the Niedermeyer approach of renormalizing, including the curvature squared terms from the start, actually does fit into a subset of this more general asymptotic safety.
Yeah, but as far as I understand, in this asymptotic safety practice,
I don't know if he's written a paper.
As far as I understand, in asymptotic safety community, what they call this term and this other term in the action, like the R squared term or Einstein-Hilbert term in the action, is just they refer to the effective action. Okay, so in this case, I'm referring to the bare action that appears in the path integral. So if I now construct the effective action, as I showed in my talk, there's a way to construct effective action, then in principle you would get all possible terms, even non-local terms in effective action. So we are talking about two different things. When you're talking about what they do in asymptotic safety and they put quadratic terms, they make a truncation, to my understanding, of the effective action where they put these quadratic terms and then maybe also the Einstein-Hilbert term and the cosmological constant. If they say, I put in the action the Einstein-Hilbert term, they mean in the effective action, I put the Einstein-Hilbert term, and then so this is a slightly different thing. So one has to take into account this difference when one compares the two approaches.
I'm a child, so maybe I wouldn't comment, but I can volunteer someone to comment on that.
Right, so the point is that, as was said, the theory space or the space that you have to consider in asymptotic safety is the one of actions that have the symmetry, which means all terms that you can write down. And then in practice, you cannot really compute in this.
Oh, yeah, definitely, yes.
You consider subspaces, and that's
it's a truncation, and okay.
It's an approximation, nothing more. But on a conceptual level, you have to consider this dimensional space.
Well, to me, is not established that it's an approximation. It's an assumption.
It is.
An approximation?
It is just, think about the theory space, don't make approximation. What the theory tells you is that you don't have to pick you don't have to choose the Bayer actions. The theory tells you which Bayer actions are possible fixed points. So there is really a finite number of choices that you can make on an exact level.
But when you make a truncation, that's an assumption, right? When you say
approximation.
Approximation.
make that point, but
oh,
why it's clear that you have to consider the infinite dimensional space.
Yeah.
Take a scalar field, compute a heat kernel, you will get all terms that you can get. That means the functional phrase gives you all the terms in general.
Yeah. So if you write just one term, you're making an assumption. See,
You're not assuming that that is the action.
Exactly.
You are saying I do an approximation and I consider only the lowest order terms and yada yada.
Oh, but then you're saying that this action can only be applied in a large distance limit. If you take just the first terms, like the cosmological constant and Einstein Hilbert term, then you can apply that. And you say these are the leading ones. These are the leading ones in the large distance limit.
No,
I mean, it depends on the expansion that you make.
It can also happen dynamically.
It could happen. It could happen, but
it can happen.
that could happen. But you have to prove it that this happens. Okay. In some cases you're so good that you can prove that all the other terms are negligible, then you have I don't know this literature.
Applies to large distance limits also.
Because
well, in this, what I'm saying is that in the large distance limit, then you have an explanation why you can truncate to the Einstein Hilbert term. But maybe you're right. Maybe there are other cases.
Einstein Hilbert, there are also calculations.
Let me finish. But maybe,
beta,
but maybe there are also other cases where you can prove that just a subset of the terms are the leading ones. And I just don't know. Okay, I trust you. Okay. If you tell me that in some cases you can prove.
I mean, there are also calculations where you study the normalization group flow for f of r. Like not to, of course, you miss the tensorial structure, but you.
F of r, you mean that you truncate the theory in a way that the effective action is f of r.
Yeah, I mean,
okay.
It is
the effective action. The effective action.
The action at any scale. In general, you have all operators.
The action at any scale. So the effective
yeah.
action of any scale.
No, even at the fixed point, you can have many terms, and this is what we expect actually.
Okay. Yeah.
Robert.
Yes, I want to finish about subject. I want to ask a very naive question that I'm very confused about. So if you start with Einstein, this is Einstein gravity, it's non-renormalizable. So therefore, you argue that you have to have all higher derivative terms. But then, if you start with this quadratic action, so with r square included and y square, then it suddenly becomes renormalizable.
Yeah.
I have a hard time reconciling these statements. What am I missing?
Because the propagator is different. Yeah, but you pay the price of the ghost, then you can control it the way you say, but you pay the price of the ghost. You have a massive graviton in the game now.
Yes, but let's see, even just from the point of view of doing naive interpretive calculations, if I start with Einstein gravity, I look at many graviton interactions and I have higher units, I generate these higher order terms. So again, it's a very naive question. So why don't I get these higher derivative terms if I start from quadratic gravity? I think you probably did the
I think because the power coming is different.
Yeah.
Because you look at the propagator, you see the way the propagator behaves on the UV, and that tells you basically that you have power counting renormalizability. Then you have to put perturbative. And if you like, a derivation of this is the modification all'orale, where by introducing Lipschitz symmetry, you have only power counting normalizability by higher special derivative. And then you don't have the ghost because you take only, but you pay the price of Lorentz breaking in the UV.
Basically, the intuitive reason is that the theory is basically the intuitive explanation is that the theory at very high energies is scale invariant, and you're writing all possible scale invariant terms. So if all counter terms are already there. In Einstein gravity, this is not true. There's no scale invariant, so you should write all possible counterterms which are infinite. The dimensional counterterms are infinite, so that's why it's not renormalizable intuitively speaking. But he gave the proof, so awesome.
Stefano.
Question on the comment concerning f of r. F of r, we know that we can map it in a scalar tensor theory, basically as an extra scalar degrees of freedom. You can bring it up and you get a particular class of non-minimally coupled scalar field. So it's a scalar tensor field. Now, in the case of quadratic gravity, you have extra degrees of freedom. You have the scalar field, you have the massive graviton in the addition to the gravity. Has anybody been able to recast it in a theory where you bring up I'm not saying just perturbatively, not perturbing around the flat background, but really in a kind of completely general way by an auxiliary variable model.
Yeah. This was done by Ovrut and others. I had the slide on this, but I skipped it because I didn't have enough time to discuss in the detail. And this paper, they extended this auxiliary field method that was used to recast the R squared, purely R squared theory, which is a particular case, of F of R, into Einstein gravity, as you said, plus a scalar, as you said, to the case in which you also have the W squared term. And they introduce some auxiliary field, which is some gamma mu nu. So it's a tensor. And in that case, you can rewrite the theory as a two-derivative theory. But you have two tensors. One is G mu nu, and the other one is this gamma mu nu. So it's similar to what you do in F of R, where you put an auxiliary field and you write the theory as G mu nu plus a scalar. In that case, you write the theory as G mu nu plus this scalar plus this gamma mu nu, and that has two derivatives.
So action, I guess, is going to be the gravity.
Right? This is a massive. You can then a combination of these two. H mu nu defined as G mu nu minus eta mu nu, and this gamma mu nu is the ordinary graviton. And the other combination is this normal graviton. This was done a long time ago.
It's just like going from second to first order form. You do Hamiltonian type calculation by introducing if the theory is under control, that should be equivalent. In this case, it's not at all. In fact, I think it's just different. If you introduce an auxiliary field in order to reduce the fourth order theory to second order theory, you can do that at the classical.
Yeah. I was referring to the classical case. Yeah.
You start introducing counter terms. What used to be auxiliary to me means it has an algebraic equation of motion, or a Gaussian functional integral, which you can integrate out and therefore go back to the full higher derivative theory. But once it starts generating counter terms involving this new field you introduced, it no longer has an algebraic equation of motion. It becomes dynamically hard. So that's a different approach to quantization.
Yeah, but people didn't look into this of extending this result, which is classical, to the quantum level, probably because it's not useful. Because the first formulation is the one that shows renormalizability. So probably it's not worth to recast it at the quantum level, the theory, in the two derivative way, because the reason why renormalizability is manifest is precisely because the theory has four derivatives. So probably people haven't looked into the reformulation in terms of two derivative actions of the theory at the quantum level, but just at the classical level.
Salvio on the study book, which did that.
Did that at the quantum level?
Well, they started looking at it.
They started looking at this, but probably there isn't much motivation to do it. But I don't know. Maybe somebody could apply it to something. I don't know.
There is a question there, or was that a follow-up? Okay, follow-up.
I mean, you never quite know when you try to recast the theory into a different form what you're going to get. And it could just be possible that with the R squared, that you end up with something, not the usual skeletons of theory you would get in the bar, but something not dissimilar to Horndeski theory, which is kind of miraculous in itself.
But Horndeski theory doesn't have ghosts, right? By definition, or yeah, so it's not possible because there is a ghost. If it doesn't have a ghost, then it's not possible.
Yeah, no, it's not.
It's a nice. It's kind of feeling.
It's
Oh,
I suppose because
you see, the problem is that on this case, you still have 3 degrees of freedom. You have the scalar and the gravity.
yes.
They always have also the extra 5.
Okay, so that wouldn't work.
If you don't have a mechanism to completely freeze, maybe, but then it wouldn't be still on this.
No, it's not possible. If Horndeski theory doesn't have a ghost, it's not possible.
But those,
Is John talking?
You cannot eliminate the ghost with the field redefinition because it's there in the physical spectrum. No, with the field that would be like saying that the ghost is an artifact.
In the sense that there's quite a lot of discussion around this, Canadian discussion. The ghost can develop an imaginary car.
Yeah, this actually does occur.
Cast it as a degenerate higher order scalar tensor theory, because those are theories that in principle have, these extra degrees of freedom, but just because you do the coefficient in such a way that you have this degeneracy, basically they do not propagate. They are there, but they are completely harmless. And the only, it would be, if what you just say, maybe selecting one of these theories where, for instance, the ghost is inactive, would be correspondent to a Vedov theory where you have exactly the combination that makes it degenerate. Just a conjecture.
It's not possible. It's not possible to remove it always. What it could be is that the ghost mass compared to the Planck mass is
Generate the order theory.
Well, these papers by Oldham and
degenerate. You mean that the Ostrogatsky theorem does not apply?
It does apply, but these are degenerate in the sense that when you look at the basically perturbation, there is a combination of the coefficient in such a way that basically you have a matrix that is degenerate because basically what is happening is that you are actually freezing the extra degrees of freedom. These are theories that in principle are higher order, and so they have all the higher extra degrees of freedom. And they are seen somehow as a generalization of this because can be reduced effectively to a scalar tensor because these extra degrees of freedom are frozen out by this degeneracy condition, by which basically the kinetic term for them is.
So I know about this degeneracy in the context, like for example, f of r. And so for f of r, the Ostrogatsky theorem does not apply because there is a non-degeneracy assumption in the theorem that is not satisfied by f of r. And this is the reason why f of r does not have a ghost. And there is a mathematical definition of the degeneracy there, as far as I remember, the second derivative of the Lagrangian density with respect to the second time derivative of the canonical coordinate has to be non-vanishing, and this is non-degeneracy condition, and this is not satisfied by f of r, and that's the reason why Ostrogatsky theorem does not apply to that case. Now I'm wondering if this.
I don't know if it is the same because in that case, in the case of Horndeski or
I'm not sure it's the same either. Yeah.
Because in that case, first of all, you are solving the problem in a sense at the classical level, and your degrees of freedom does not act anymore already like from the start. While in the case of quadratic gravity, so when you get log corrections, those are quantum corrections. So from the start, you would have a theory with a ghost, unless you cure it using some prescription. but then you get the quantum corrections like log of box, and that creates an instability, but the degree of freedom is still there. So the mechanism is slightly different, and that's because of non-locality, while in the case of Rorschach or Troca is because of local terms of higher order.
Yeah, but in fact, I'm not talking about on this anymore.
Okay.
About DOS.
Okay.
So it's
What
like
is
I
that?
think you can generate it by applying this Fortnite transformation to this, if you. But anyway, these are higher order degenerate scalar tensor theories, and I think that I was just conjecturing maybe that what she was saying could be done with this case, because there you are basically a tuning of the coefficient of the theory in such a way to not propagate the extra degrees of freedom. That's the core of the idea, and you remain just with the scalar and the graviton, which are harmless from that point of view. So, and maybe that if you can find if you can start from a quadratic theory which is empty and then map it. You will find out that you cannot undo the degrees of freedom.
This is very unlikely.
The representation you use in the theory, But you may have that the empty theory is basically one that has a frozen extra degrees of freedom associated with the goals.
Yeah, but it's a different. It is a different.
In general, the coefficients
point,
are running here, so a tuning of the coefficient, like in some subsurface, will be unstable under renormalization. So, yeah,
exactly.
if you don't have a symmetry.
You have in this theory that you have some symmetry protecting the coefficient. So that is a requirement, But
yeah, probably this could at best happen in some limit, like low energy limit or high energy limit. Probably doesn't happen for any values of the energies.
It is non-trivial.
Yeah, but to me, there's no extra symmetry. Yeah.
Exactly built in such a way that there is kind of protection.
There is a new pointer.
Well, my question will be the following. You have mentioned the second scale. Which is much less than the Planck scale. So the question is, what is the reason for this second scale? Can be related with breaking of some symmetry, for example, breaking of Lorentz symmetry, something like this.
Yeah. So I mentioned this intermediate scale lambda g, above which gravitational interactions are suppressed. And this is somehow intermediate between the electroweak and the Planck scale in order for the Higgs mass to be natural. And actually, at the end, I also discussed that for this value, the maximal value compatible with naturalness, then you get a selection of these isotropic homogeneous species. Now, I mentioned this symmetry that corresponds to setting this intermediate scale below 10 to the 11 GeV, and this is the shift symmetry of the Higgs mass. The reason why the Higgs mass turns out to be natural in this case is that there's an approximate shift symmetry on the Higgs field, and this is the reason why quantum corrections then preserve the smallness of the scale compared to the Planck scale. So the answer to your question is this shift symmetry.
More questions? Stefano.
Concentrated much of your attention concerning the phenomenology, which is the topic of this week on cosmology. Can you elaborate a little bit to what we know from black hole coalescence on this subject? I mean, for sure, you have, for example, an extra degrees of freedom with the waveforms, the polarization. In a certain sense, you see, this is completely a different energy scale with respect to the one you consider in your talk. So I was curious to see if there has been work to relate it to, because we have a lot of information about that.
So what the information we have is about these astrophysical black holes, and at that scale, the theory is just GR. So the predictions are the same, but
the scalar degrees of freedom. The
scalar degree of freedom is at a very large energy. So I put the scalar degrees of freedom at a very, very large energy. So this is an extremely small scale modification of the theory. This is a macroscopic modification of the theory. The astrophysical ultra-compact objects should be the same. But the question is, to me, is more what happens to the central singularity, which is then orthogonal to probably to phenomenology, because you cannot access that. But probably is there that you can see that there is some difference, because in Einstein gravity, you have basically nothing prevents the gravitational collapse, and at the end you get the singularity. But in this theory, you have a softening of gravity at a microscopic scale. So eventually this gravitational collapse should stop, because at a very microscopic scale, and you should see somehow some finite distribution of mass at the end, which is microscopic. Because, as I said, the theory eventually becomes softened. So at the end, the gravitational collapse should stop. So this is maybe the way the central singularity is removed, but no explicit calculations have been done on gravitational collapse. So
because you will have some of these.
if you put the coefficients to extremely, so the coefficient of R squared, if you put the coefficients of R squared and W squared to an extremely large value, these are dimensionless coefficients. If you put an extremely large value, large enough, then you get modifications. But those are not the values I'm considering.
There are modifications, but they're out from the range, the modification you could get.
The range I'm considering, because there's no motivation for considering that ranges.
Oh, well, yeah.
Yeah.
Follow up on your answer. It's not true that, I mean, what you say, I understand what you say, but I just want to give a glimpse of hope. When I do regular black hole, in order to describe a black hole which doesn't have a central singularity, just based on the prejudice that somehow quantum gravity has to solve the problem, then you generally replace the Schwarzschild mass, the ideal mass M, with some M of R, which at infinity should be the ideal mass. This M of R, if you scale at least like R cube for small r, gives you that the curvature goes to 0 at the core. So what is happening is that is happening something which is very much in your spirit, although normally what you get is a de Sitter core. You have a de Sitter core, an inner horizon, and an outer horizon. These are the generic form of any regular black hole. There are another class that are even more exotic, but it might be for another discussion. But just what I want to tell you is that if you compute the Einstein tensor of these black holes, it's never 0. What it means that if you try to say, okay, I have this solution justified by quantum gravity effect, in your case, the softening of gravity, and then I put it back in the Einstein field equation, given that I don't know, as in your case, instead you have the full theory. I put it back, it gives me an Einstein tensor, which is never 0. It's not a Ricci flat solution. The stress energy tensor is non-zero. It's a energy condition violating at the core. Otherwise, it needs to get out of the Ferrous theory. So what you get is that this stress energy tensor doesn't go to 0 at the outer horizon. It has always a tail, because naturally you wouldn't get the step function. And what is happening is that, for example, if you look at the quasi-normal modes of this black hole, they can be very similar to the one of a Schwarzschild black hole of GR, but they are never identical.
These are other cases. You're considering some other theory. This is not quadratic gravity, it's some other theory.
It's even more generic. It's assuming that gravity gets weaker at the core. Basically, you get a regular core. You just ask a very simple question. I want to get out of Ferrous theorem. I want to defocus the geodesics in such a way that the first part of the Ferrous theorem is not there. I don't have the focusing point that then I demonstrate it cannot be part of my spacetime. And then you just very generally ask what can happen there. Basically, half of the scenario are a scenario like the one I just said. You can have a de Sitter or anti-de Sitter core, an inner horizon, an outer horizon. these black holes are never identical to GR black holes. So it's not true that what happens at the core cannot be seen outside. This is just standard law, which is not supported by any things that is our core calculation. And it is even worse than that because you have an inner horizon. This inner horizon now is coming way in all the possible ways that is unstable.
Yeah, but also in quadratic gravity, you can put the coefficients, as I said before, you can put the coefficients to some values that you can see the modifications.
No, but this is worse. Even if you put the coefficient in such a way that the modification happen only at Planck densities, still you get a structure which is not the GR black hole, which is good.
At Planck densities, yeah, at the Planck scales.
But you see, you're reasoning about the standard law
So you mean that everything we know is finite, it will be different.
No, it will be slightly different.
Slightly different, yes,
But
sure.
You see, you don't need the Planck physics. What is wrong is the idea that you need Planck physics.
I didn't say that. I didn't say that you need Planck physics to.
That the regularization of the core cannot give an effect outside of the outer horizon. There is nothing propagated. There is simply a different.
But I didn't say that you need the Planck physics to get a modification.
No, you didn't say that, but you say, given that the modification happens at the core, you say this probably has nothing to do with phenomenology because it's happening behind the horizon. What I'm trying to say,
modification of what? You say
physics, because you say the softening of gravity, the fact that they don't generate a singular core, cannot be seen outside of the horizon. What I'm trying to argue is that all the evidence we have so far is that in principle you have a different geometry which has a different.
Yeah, this is true, but yeah, but what I'm saying is that experimentally, observationally is probably difficult to see the differences in this theory.
Signal to noise ratio of 100 with LISA, and you will have many events in the sky that you can see. Statistically, you can start to play this game. And so it's not completely hopeless.
Yeah, but I also would like to add that in various theories, I mean, even if you have effects suppressed, and then, I mean, of course, with some high energy precision, you can discriminate between stuff. But in the case of quadratic gravity, in my opinion, the effects will be even more amplified because you have two more degrees of freedom in the theory, the ghost and the scalar. And if you take that seriously, then you can have like additional waves on top of the gravity wave. And this is actually the content of a paper by Javier Calmet, free waves for quantum gravity. So if you take the quadratic gravity action with log corrections, you get modifications to the what you would
there are modifications, but they are tiny.
Because it's saying the energy of the gravitational wave you see are smaller, they're below the kilohertz in electron volt, they are very tiny. So what is happening is that it's saying if my new physics is coming, but you see, for example, your new physics, for what I was saying, is still very interesting because M2, I mean, the scale at which you had the graph when you start to see the solid state, that is not the Planck scale. So your new physics will kick in the collapse. You form the outer horizon, you keep collapsing well before you get to the Planck density. And anyway, Planck density is not Planck length. It's not a Planck length radius core. Planck density is much larger than it is. So, but in your case, you don't need to get there. You need to get to the scale in which where you start with the deviation from the GR behavior. That is where your gravity starts to be weaker. So your core size is not going to be Planck scale. It's going to be larger inside the outer horizon, so you will see still probably a black hole, but that black hole will not be a GR black hole. When it resonates, when you have quasi-normal modes, you may have deviation, and you may cast at least a constraint on the parameters on your amplitude. I think it was included. So that you can cast a constraint with the sufficient statistics. So I think that there is a window that quantum gravity technology which has to be used, and it's just standard law that whatever happens behind the horizon stays behind the horizon. This is not a flight level. It's the old space-time.
No, I'm not saying this because, for example, there are these solutions found by Holden and Wren of spherically symmetric solutions in the presence of have some matter density, and they found that there are solutions that don't have horizons at all in this theory. So they say that there is a modification, not necessarily just at the core of the compact object, but also the horizon scale. So this is, in principle, is possible. It'd be fantastic.
No, you can have echoes, for example. When you form one of these objects, given that there is a core that can be traversed by the gravitational waves, you have a part transmitted at the external potential. Once get through the center, gets on the other side, and you get echoes. The echoes can give you a lot of information about the structure of the core. So again, I think that these are all opportunities. It's not true that.
Yeah, what I meant before is that what happens inside the horizon is not accessible. This is what I said before. No, I didn't say that if a modification of the core of the ultracompact object occurs, then there is no modification outside the horizon that maybe is visible. That is accessible, yeah. But what I'm saying is that you cannot go at the center. You cannot access with the current observations the center of the black hole. This is directly probe that.
It's still reconstructed.
Yeah, indirectly, yeah. In a given theory, yeah.
So these objects that call them two stars, I think, yeah. So does he resolve the singularity, or it's just about the one of horizon, risen horizon, and the singularity?
In that case, they are naked singularity.
Yeah.
Yeah, the astrophysical ones that Haldom and Rand found have a naked singularity at the center. And then I had to skip it because I didn't have time. With Verme, I computed what happens to ultracompact objects that have scale that are microscopic compared to the scales of these extra degrees of freedom. And there is a linearization mechanism there. You can study these objects with the linearized theory. And in that case, if the source is non-singular, then you get a non-singular ultracompact object that is also horizonless. But we could not go to the astrophysical size because at that scale, the theory is not, it's not possible to analyze the theory with linear theory.
I have actually follow-up on that. I mean, in quadratic gravity, so quadratic gravity is really your Bayer action, your fundamental action. But in quadratic gravity, there is a complete classification of how modified black hole solutions look like close to r equal to 0, and there are singular solutions. So there actually Kelly worked a lot on that. We typically say that quantum gravity should resolve singularity, so this does not happen in quadratic gravity. You would need matter for singularity resolution, right?
As far as I understand his papers, yes. I mean, if you don't put any source and you just look at the equations in empty space, then so far they just found solutions that have singularity at the center. But this
like r squared. So there's no inverse r, but it's still singular.
It's still singular. So what they found is other solutions different from Schwarzschild solution, but are still singular in the center, in the vacuum. Now, what I expect is that, as I said before, that in this theory, since there is this softening mechanism, what is more physical is actually to consider an extended source, because it's true that this gravitational collapse in astrophysical setting will occur because the theory is basically Einstein gravity at large scales, but then eventually the gravitational collapse should stop when the size of this matter density goes below this critical value, which is 1 over lambda g. Lambda g being the energy scale above which gravity is softened. So it seems to me more physical to consider these extended sources rather than quadratic gravity in empty space. But what one should really do is to compute the gravitational collapse to check all these properties. And this hasn't been done, to my knowledge, so far. So this is
But
one of the
I mean,
interesting.
the solution you converge to should really come also from the field equation of your theory.
Yeah, you
And,
should follow the gravitational collapse and
not even, I mean, the outcome of the gravitational collapse must still be a solution to your field equation, so you can avoid to complicate your
everything
life.
should be a solution of the
Yes,
field
but
equations.
the field equations in your case are essentially quadratic gravity with some form factors. And my point is that close at high energies, you have a theory that is local, so you don't avoid getting singular solutions unless you have matter that makes the job.
Yeah, I mean, they didn't find any black hole solutions that don't have a singularity in the center, but there's no theorem that there is no black hole solution that don't have a singularity in the center. So it's just this is just an outcome of the numerical search.
Means that your theory admit solutions includes a solution that are singular. There is first Stefan and then Benny.
This respect, even in GR, there is been a calculation where you take, you find the semi-classical solution which are self-consistent. So they don't form them by producing by looking at a collapse. They just ask if they can find a vacuum state such that it provides a vacuum polarization such that stabilize and creates, I don't know, a regular black hole solution, or an ultra-compact object which is stable and not singular. And they found that there is papers by the group of Baxero in Granada, where they found some of these solutions. The ultra-compact one are particularly interesting because basically you have a regular object everywhere, almost a black hole, very different. I mean, very difficult to distinguish from a black hole, if not by, for example, this story about the echoes. But then if you look at the echoes, you find out that the structure of the core, which is an anti-de Sitter core, is such that basically they get delayed so much that for us it would be almost impossible to see. So they are very, very difficult to distinguish with a standard black hole. And they are just self-consistent in classical solution.
This is GR or?
So you have a star, and you stabilize the star by finding a vacuum state in that geometry, which is consistently stabilizing it.
But what is the self-consistent stabilization mechanism?
It's basically vacuum polarization. You have a vacuum.
Okay, yeah.
That as the polarization is opposing the formation of an horizon. If you like, it's very simple to conceive how this happens. If you know a little bit the vacuum states around black hole, if you take a star, the normal vacuum state would be Bulwer. Bulwer has a divergence in the stress energy tensor that goes like 1 minus 2m over r, or everything squared. And that basically tells you that if you try to take a star and almost semi-statically to form a black hole, you will have a huge vacuum polarization opposing the collapse. Normally, the collapse generates an horizon because in free fall, you start with Minkowski. There is a theorem, Sweeney-Wald, the theorem that tells you that you can keep renormalizing in the local inertial frame. The stress energy tensor never grows so much. You cross the horizon, then the only non-singular state that you can build is Uru, which is the one predicting Rocky radiation at infinity. It's very simple, but if you take a star and try to find a step, imagine you can spot it as something that is a black hole, you can, because you are in the Bulwer state, you have this growing divergence, and that will try to oppose to the formation of the horizon. So you can find self-consistent ultra-compact star solution supported by the vacuum polarization in principle. The difficulty is to create them by a suitable mechanism of collapse. It cannot be a standard free-falling collapse, probably. Another idea is that you form the core, you form the horizon, you form the core, and then you have a bounce, and you have multiple bounds that stabilize on this horizonless structure. But I mean, this is another story. Just telling you that in GR, there are self-consistent in semi-classical gravity, so they have a stress energy tensor to answer your. They are not really they are vacuum solution, but there is this vacuum polarization that the expectation value is non-zero. The classical one is zero.
Yeah,
so in our language is not vacuum solution.
The classical one because they have the matter of the star.
Yeah,
in our language, this is not vacuum solutions, no? That if the energy tensor is not zero.
Exactly.
This is not
the ultra-compact star. So the classical stress energy tensor is the one of the star. But in principle, you should be able to do the same.
Yeah.
Implying the
But I think in GR will work differently than in quadratic gravity, but I don't want to speak because of that, and also because in GR, so you're talking about vacuum polarization effects, so in GR you would naturally generate them, while in quadratic gravity, so the idea, since it is perturbatively renormalizable, you wouldn't generate more than what you have, you only change the coefficients, and therefore you essentially get what you have.
But that is then that the vacuum polarization is not, I mean, even if the theory is renormalizable, you would expect that you can have very large vacuum polarization in some structure, right? I mean,
Potentially.
you see, what I mean is that it's dangerous because there are, it's a kind of consistency that then when you form the horizon, you must be in Uru in order to have a non-singular state. If a bulwark is non-singular in quadratic gravity, then nature doesn't know how to choose the vacuum state once you form an horizon.
I'm not saying that I like. I mean, it must be more complicated than in GR, I think. And I have naive expectations that. And I have naive expectations that there are still singular solutions. That means if in quadratic gravity you want to resolve singularity, that maybe you have to rely on matter.
You have to put matter probably, but I don't know.
Benny had a
comment. Related comment, remark, or whatever you want to call it. The question that you could ask is, the first question you can ask is, does your theory have non-singular solutions? And the second question is, should it only have regular solutions? And I think quadratic gravity kind of falls somewhere in between, that you definitely have the action, the solutions to GR as solutions by construction. And that's kind of unique to quadratic gravity, because as soon as you add generic 6 derivative terms, this property is just gone. So what's your...
So again, this is basically what I said before, that you should be in some physical setting where you have some initial matter distribution and follow gravitational collapse and see what happens. And if you do that, my expectation is that eventually the gravitational collapse stops because you have this softening of gravity, and then there is some finite distribution, although microscopic, of matter. And then you should, if this is true, you should rather look at the solutions that are not in the vacuum, have a non-zero energy momentum tensor. And then in that case, you don't know if the solutions are the same as in GR. Okay. Yeah, probably not. Yeah.
More questions? Well, perhaps we could go back to one of the points that Mairi raised during the talk, so namely inflation and quadratic gravity being either a theory or a model. Perhaps now we can comment more extensively about that.
Yeah. So I've been discussing with him during the coffee break. So what I mean is that if you start from an initial condition, which is the most generic one, where you have all possible values of the metric and the scalar field of the inflaton and all other matter fields that you have, then you need to live in those patches that are enough homogeneous and isotropic, because enough in the sense that I specified during my talk, because otherwise you trigger these runaway solutions. If there is some dynamical mechanism that avoids this, anyway, you should dynamically go to enough homogeneous and isotropic patch. Now, this is an anthropic explanation of a homogeneity and isotropy. It's not a dynamical mechanism necessarily. So it has the you can criticize this by the usual criticisms that are raised to anthropic reasoning. For me, it's an explanation, though.
I think that as long as you are not able to prove that a bubble of the universe, of what is a bigger universe, that remains a claim, which is not without any value, but it's a philosophical claim, so a postulate. It's not a scientific explanation. So that's what, if I understood, she was pointing out.
Let me say what I was pointing out.
No. If it's that, I kind of agree. So it's not that it's not without value, it's just that it's not scientific or more fundamentally scientific than other.
For a theory to be scientific, to my understanding, is not that a theory to be scientific does not have only to predict testable things. Yes, it has to predict some testable things. Even the standard model predicts untestable things at very high energies that you will never be able to test. So this doesn't mean that the standard model is not a scientific theory, because it has some predictions that can be tested.
Yeah, but at the moment, you have some other prediction claims that quadratic gravity is the correct theory. So that one still.
Well, there are some predictions, but they are not for the future. Yeah, they can be tested in the future. Yeah.
But even if they will be tested in the future, so quadratic gravity will be the definitive theory of quantum gravity. The part where you say that we live in a bubble that is
probably cannot be tested. Probably cannot be tested.
That's remain a postulate. As far as you cannot.
Well, it's not a postulate. It's not a postulate. It's not a postulate. It's a consequence of the theory. But I agree with you that most probably you cannot test that there are other.
Because that is okay. I mean, also general relativity has pre-postulates. It's not that postulates are bad, but they're philosophical. There is a degree of arbitrariness that cannot be reduced with the quantitative experiments. So it's a postulate, it's a philosophical postulate. But it's okay. I'm not saying that.
I don't agree.
It's not like scientific prediction of your theory.
If you define a scientific prediction of the theory as something that can be tested, then it is not a scientific prediction. But with this definition of scientific prediction, yes.
Yeah, but also in general, you cannot always test directly assumptions, but you can test the consequences of these assumptions. And if the consequences work observationally, then perhaps it is an indirect test that your starting assumptions were right.
I completely agree. That's why postulates are not useless, but they are postulates.
Can I try to say at some point?
Okay.
At some point, I would like to say again what I was saying, because
I wasn't sorry, I didn't mean to take your opinion. It's just that I was interested in that.
It's fine, but let's say what I was trying to say. I was trying to say that inflation has been generically standard inflation to a method of thinking. It's been always seen by considering the background which is homogeneity and density. The discussion was about the homogeneity. I thought that you can be particle creation. So it has been more than 30 years ago, a work by Milan and Godwin was a numerical kind of study, whether you can have onset of inflation if you have initial conditions which are not here. And almost about 30 years ago, 25, 30 years ago, we did an analytical study with the Esteban Calcetta, and we saw indeed that if you have initial regions which are not homogeneous to about several horizon lengths, you cannot have the onset of inflation. So the question is that a kind of good starting case for the semi-classical gravity at the end of the quantum era? Is an open question, but this is a requirement for the initial conditions so that inflation can take place. So this, for me, it is a constraint on inflation by meaning inflation to the scalar field. That's all I wanted to say. that it is known from long ago that if you do not have homogeneous kind of regions, inflation will not start. That's all. And for me, this is a requirement for inflation, which might be the final kind of initial condition. I don't know. That's all.
Yeah.
Nothing more, nothing less.
So what I'm saying is, in this theory, on top of that, you can only live on those patches where inflation can take place, while in GR, this is not necessarily true. This is what I'm saying. So, yeah.
Should that be another condition for these theories, or you want to present it like these theories, require such a condition, so it go hand by hand with the onset of inflation?
Well, it is the most generic initial condition, where the fields can acquire whatever values you want in a given.
Say that this class of theories, this class of models, but probably are not the physical one. So it is another requirement for these models, theories, whatever you want to call it, to work. So either you can consider it like a limitation, or you consider it like a prediction, or how do you see that? Is it consistent with your model?
It's not, so I don't see it as a requirement for this theory or model to work. I don't see it like this. It's just, I take an initial condition which is completely random, like in Linde's sense. And then in this theory, you can show that only in those patches that are enough homogeneous and isotropic, you can have life. And you can live.
Robert, the follow-up and raised his finger. So
with this discussion a little bit, after this afternoon, I will try to argue that let inflation rest in peace.
okay. Short follow-up and we close.
It's that, you see, to me, it's not the problem that your theory say only life can develop in the patches which are. I mean, I have many patches of without the possible value. I have some which are homogeneous and isotropic. There, inflation starts, and there also the theory is such as the parameter such that the life can take place. This is basically what you're saying.
Yeah.
But you see, from the point of view of predictivity, this is not really predictive. You can say that this is self-consistent. It's not the fact that there exists life that doesn't contradict your theory. The problem is your theory predicting that the patches from which inflation can start are generic or not?
The theory predicts that the patches where inflation can start are homogeneous and isotropic, or they are dynamically attracted to the
time, not that you need homogeneity in order to start inflation. The problem is that then people say, oh, but then I need to start with very special conditions to start inflation in the first place. So it looks like a circular argument. So the problem.
No, but this is a different statement, because in a generic theory, maybe you could also live in a patch where inflation does not take place.
Can you define again? What do you mean that we can live?
Sorry?
What do you mean that we can live that life will start? What do you define as that? You define that inflation will take place, or something more important? When we live, we have to.
Because something more important, that the Ostrogansky instabilities are avoided. Not only that, so those patches where inflation takes place are also those where Ostrogansky instabilities are avoided.
The class of theories that you present are not physically, correct, because this is your class of models that wants this kind of stuff. So I can say that your starting point, this is a counter argument. For you, it's a consistency check. But it might be that at the end of the day, if I have a quantum gravity theory that tells me that I cannot start the semi-classical gravity with this kind of patches to be homogeneous and isotropic, then I have to prove that this class of theories that we presented are out.
Okay,
to use
so-
the consistency check, I think we have a kind of semantics argument here.
which we can continue during the panel discussion today that I think will be on quantum cosmology. So for now, I would also, because we are running out of time, I would close the discussion. Let's thank again the daily speakers. And